Hello, this is the next video in a playlist that I'm calling hypothesis testing, and here we're in the unbiased hypothesis testing phase of that playlist. Now in previous videos we've looked at uniformly most powerful unbiased two-sided simple versus composite hypotheses, and this little playlist we're doing is in the composite versus composite hypothesis testing. And so we're going to be in the binomial setting. And I encourage you to look at this video first, because that's where we cover the theorem that we're going to use for this test. Now, after I conduct several examples, we'll go back and prove that, but I want to do the examples first. So the setting is this, that our data follows a Bernoulli, right? Or it's either 1 or 0 or yes or no. It's a dichotomous response. We take a sample size n, we're going to test at the alpha level, and the null hypothesis is that the true proportion is between some, between P1 and P2, some values, versus the alternative that it's strictly less than that P1 or greater than that P2. Now the Bernoulli can be has a probability mass function like this, and it can be sort of manipulated to look like the exponential form. So if we take the 1 minus P and put it here, and then the minus x, we put it in the denominator, and then we have to take the e to the log of that to make it look like an exponential form. Then this is a function of just a parameter, this is a function of x's and the parameter, and then the function of just the data itself, or the x's, is just 1. Now here, if we call this natural log of p divided by 1 minus p tau, then this is the exponential form. And the test statistic is the sum of the x's. So let's just call it y. And the sum of Bernoulli's we know is a binomial in p, sample size n and same parameter p. But note that the natural log of p divided by 1 minus p is a 1-to-1 function of p. Where of course p is a proportion, between 0 and 1. But you can also back solve for p to be equal e to the tau 1 minus e to the tau. And so they're 1-to-1 functions of each other. So tests for tau and p are 100% equivalent. And so the UMP test is given by this test function phi. It's a 0 if our test statistic, the sum of the y, that should be the sum of the x's. And so then, 0 means we do not reject, and then it's gamma 2 if C2, if y is C2, and it's gamma 1 if y is C1, and those are our cutoff values that we're trying to determine. And if it's 0, it means do not reject. If it's a 1, it means absolutely reject. And if it's a number between 0 and 1, it means reject with that probability. And the test function is a 1 if it's less than C1 or greater than C2. Now C1, C2, gamma 1, gamma 2 are determined by these equations. The expected value of our test function, assuming P1 is true, is alpha, and P1 is determined by that value. And of course P2 will be this value in the next equation. The expected value of our test function, assuming P2 is the correct proportion or probability, is set that equal to alpha. And this is it. This is the UMPU test, uniformly most powerful unbiased test. So let's start solving for these. So the first equation is alpha is equal to the expected value of the test function, assuming P1 is true. And since this is discrete, the expected value is the value times the probability of happening. Well, that's just 0. So then it looks like we take a 1 times this probability, which is what this is here. And then it's gamma 1 times this probability. And then it's gamma 2 times that probability. Now what I do, I should say, is I take that and subtract it to the other side, take this, subtract to the other side, and then leave these just come down. So this is what we get. We're going to call this value K1 this value K2, not the gammas, and then this value K3. And the reason I do that, we're going to use it in the next video where I do an R illustration of how to calculate C1 and C2. What I do is I create a matrix of all possible C1 and C2s that could be rejection regions. And then so for each row, the C1 and C2 are known. So then that creates an equation of, using both of these conditions of two equations, two unknowns. And then it's actually straightforward to solve for gamma 1 and gamma 2 in that setting. So if we look at the second condition, and then the expected value of this, assuming P2 is true, is this. So this is 1 times that probability, gamma 1 times this probability, gamma 2 times this probability, and then it's 0 times that probability. Since it doesn't factor in, we're not going to add it. Then I subtract this to the other side and this to the other side, and that's what the K4 represents. And then this comes down, we'll call that K5, and then this piece K6. And then using R, once you have that matrix of possible C1 and C2s, then it's just instant. Because when you back solve for gamma 1 and gamma 2, only, it's part of a test function. So gamma 1 and gamma 2 have to be between 0 and 1. And there's only one equation that will work. It's a unique solution with probability 1. So to use R, we're going to generate all possible C1, C2s, solve for gamma 1 and gamma 2 such that they're between 0 and 1, and boom, we have our rejection region. And now whenever people think, oh, binomial, use the normal approximation. Well, in short, it doesn't work. But let me quickly go through it. We know that, the mean, so the mean of our Bernoullis, if we subtract the true proportion divided by the true standard deviation of y bar, it limits in distribution to a standard normal. Pictorially, it looks like this. So we have a normal distribution over P1, P2, there's a little normal distribution. But note that the curves are not identical. So the variance associated with this one is different than the variance associated with this one. So when we go to calculate these probabilities using normal, it's actually much tougher than what we've done before. You can do it, you can solve for it, you have to use a computer, but you can solve for it. But then if you have to go to the same effort to just solve the exact using the binomial, why not just use the binomial? There's no simplification. And so this is sort of a silly method. And I almost didn't put it, but I wanted to illustrate, because a lot of people think that, oh, use normal approximation. But my test, and I don't know if I should call it my test, the leave out one tail test is this. And now I've never seen this test before. It's probably been done, I'm almost certain, but I've only seen it when calculating sample size for power calculations. You leave out one tail because it probably, if you assume the true values somewhere in the alternative region, one of those tails that has really close to a probability of 0 of happening. So you just leave it out and it makes everything easier. So you set alpha to the probability of being left. So it's probability our test tick is less than y1, C1, and then it's y equal to C1 with this probability gamma 1. Now it's easy because you start picking C1s, you increase until this goes over alpha, and then you back it down 1, and then you solve for this using, then this is known, this is known, this is known, so you can solve for gamma 1. Subtract, divide, boom, there's gamma 1. And then you do the same thing for gamma 2, assuming that P2 is the true probability. And you can solve for these with a simple calculator and the back of a book that has binomial probabilities. It is so easy to solve for. The computer's not needed. But it's only approximately UMPU test. And we'll illustrate that in the next video when we do an R illustration of this specific example. All right, well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.